Hi everyone, I'm Lauren Budorick and I'm on the Mapbox GL team here. So we build Mapbox GL JS and Mapbox GL Native, which are our client-side map renderers for web, mobile, and embedded devices. And today I want to talk about how to draw a map. So there are two things I want to convince you of today. One is that maps are pretty hard. They're kind of taken for granted, but there's a lot of complex systems behind it. But at the same time, maps are not magic. There's kind of some beautiful math and geometry and logic, and I think it's really exciting to figure out how it works. So why do we care about Mapbox GL maps and client-side rendering? Client-side rendering enables much more powerful and flexible maps than we ever had before. So previously, in the world of raster maps, we just delivered static image tiles to your device, and that data and that style was all you got, and if you wanted to change the data or change the style, you had to request new tiles from the server. But with client-side rendering, by separating the data from the style and delivering both to your device, you can have really dynamic maps packed with huge amounts of data. So now that we have all of the data you could possibly want in your map without showing it necessarily, but building a really powerful renderer that can change the display of that data in a matter of milliseconds, you can build really dynamic experiences for your users. So today, first I'm going to talk about some terms to make sure we're all on the same page, how graphics engines work in general, and finally how Mapbox GL is really just a graphics abstraction layer for map designers, and how Mapbox GL style sheets map to rendering paradigms. So first, some definitions. The GPU is a graphics processing unit of your computer, so that is as opposed to the CPU, the central processing unit, which does most of the heavy lifting. The GPU is less good at huge, complex tasks, but it's really good at doing lots of small things in parallel, for example, computing and shading pixels, so it's great for graphics. OpenGL and WebGL are Open Graphics Library and Web Graphics Library. For all intents and purposes today, we'll consider them two sides of the same coin. These are programming APIs for developers to be able to access their users' GPUs and program for their graphics cards directly. And vector maps are another term for client-side rendered maps, or Mapbox GL maps, for example. These are maps drawn on your device by your GPU. So all the things I'm going to talk about today are specifically GPU rendering techniques. So you can also render on the CPU, and that's what we do for a lot of raster tiles, but we're going to talk about GPU rendering today. So how does graphics programming work anyway? I want you to think of the single high level of unit of graphics as a frame. You can think of a frame in graphics much the same way you would think of a frame in video. So every time you see anything change even slightly, there's a new frame being drawn. So whether the whole thing gets recolored or something just moves over by 1 pixel, either way, the graphics engine behind it has to request a new frame and draw everything within it all over again. And a frame is made of a bunch of individual draw calls. So a draw call is when you give the GPU a specific set of programs called shaders and a specific set of geometries, and you ask it to draw the geometries according to the instructions in those shaders. And you can have a ton of draw calls within one frame. And the geometries, in almost all cases, are going to be triangles. The thesis behind that is that the triangle is the smallest two-dimensional shape, so with a triangle, you should be able to make up any kind of 2+ dimensional shape. You're going to have to trust me for now that that's true, but I'll show you some examples later. So let's walk through how that works in practice. Say you want to draw a really simple triangle. So here I've set up 3 corners, or vertices, of this triangle, and I want to draw just one triangle between them. You'll note that the coordinates here are between -1 and 1 inclusive. That's because WebGL screen space, or clip space, is between -1 and 1 and the x, y, and z dimensions. So if you want anything to show up on your screen, its final position has to be between -1 and 1 in the x, y, and z dimensions. You'll also note that these are just x and y coordinates. For simplicity's sake today, I'm just doing it in 2 dimensions, but really, with any kind of graphics API, you generally get 3 dimensions. So now we add these vertices to the vertex buffer. The vertex buffer is not really anything fancy. It's really just an array or a buffer in which we can put all of our vertex data. And then we set up another buffer called the index buffer. And the index buffer is going to tell the GPU which vertices to connect to make triangles. So the values in the index buffer are triplets of indices into the vertex buffer. So by using indices, we don't have to render consecutive vertices, and we can use vertices in more than one triangle. So now we have 3 vertices, and we know which ones to connect to make a triangle, and we can draw. So I left out the part here that decided that the triangle should be fully opaque white, but that happens in the shaders, so let's talk about that now. So what if you didn't want it all to be one color? What if you wanted it to be a gradient triangle, and then these two will be purple, and maybe that vertex will be aqua, and you want it to kind of interpolate between them? Because I want the colors to vary by vertex, I have to attach new data to each vertex in my vertex buffer. So I've added more vertex data here and updated them in the vertex buffer on the left. I'm using these 3 extra numbers to represent RGB colors. The purple in this case is half of the red channel, none of the green channel, and full blue, so it's 0.501. And the aqua is no red, full green, and full blue, so that's 0, 1, 1. I also want to point out that we can name the separate parts of the data in each vertex. So when the data is going to be read by the shaders later, they're called attributes, which is why I'm choosing to prefix them here with A for readability. So the first two components of each vertex represent a 2-component vector called A pos for position, and the last 3 components represent a 3-component vector called A color. This is a lot easier than if we had to remember which data was where in the vertex and then access them by index. So here's a pretty simple example of a vertex shader. There are 2 shaders that you need in order to draw. So there's a vertex shader and a fragment shader. The vertex shader goes first, and it runs on every vertex in your vertex buffer. And its responsibility is to output the final position of that vertex in WebGL clip space. So you can see here I've declared 2 attributes. These are attributes that I expect to be able to read from each vertex, the position and the color, and a varying, which I'll talk about in a moment. And then we have to declare the final GL position of this vertex in clip space. So the first 2 X and Y components come from the position attribute, and then the third component I'm setting to 0. That's our Z coordinate, because we're ignoring Z for today. The fourth component is the W coordinate. Kind of just don't worry about it. It's a kind of trick to make linear algebra work better. And then, the V color, like I said, is a varying. Varyings are how we can pass data from the vertex shaders to the fragment shaders. So since we want the color to be accessible by the fragment shader, we assign it to a varying here. And now that the vertex shader has run on all the vertices in this draw call in parallel, in this case there were just 3, but there could be many more vertices that are running in a single draw call. Now the GPU will rasterize these final vertex positions according to the GL position, and figure out a list of every pixel or fragment in between those vertices that make up each triangle, and hand those fragments off to the fragment shader. Now the fragment shader will run in parallel on all of the pixels or fragments in each triangle. So here's an example of a fragment shader. The responsibility of a fragment shader is, as it operates on every pixel, is to determine the output color of every pixel. So the cool thing about varyings, by the way, that I didn't mention before, is that they naturally interpolate between the values assigned to them at each vertex. So remember, we assigned color to these varyings at each vertex. So one of them would have been aqua, and then 2 of them would have been purple. But then at any given pixel in between those vertices, it's going to be interpolated somewhere on the aqua-purple spectrum. So now I use that RGB as the first 3 components of the output vector, and then assign the alpha to 1 for a fully opaque triangle. And then we draw this gradient triangle. There's one other thing I want to take a few minutes on, and it's space and coordinate systems. So we've already established that WebGL clip space is from -1 to 1 inclusive in the X, Y, and Z dimensions. Again, we're ignoring Z here for today. But what if you have geometry coordinates outside of -1 to 1? How do you make those show up on your screen? And in practice, this is almost always going to be the case. So say you want to draw this triangle, and the coordinates you have are between 0 and 10 inclusive, and you want to draw this on your screen. But if we just try to draw those coordinates in WebGL, where here the pink square represents WebGL clip space from -1 to 1, you can see that they all fall way outside of this range, so we wouldn't actually see anything. So somehow we need to map all of the coordinates in our coordinate system into a different coordinate system. So the corners, 0, 0, 0, 10, 10, 0, and 10, 10, will become the corners of WebGL clip space, -1 to 1. And then presumably we can also use the same technique to map all of the vertex positions to new vertex positions in WebGL clip space. So we have to figure out a way to transform our coordinates so they all basically do this. In our new screen space dimensions, the vertex 5, 10 will become 0, 1, 7, 5 will become 0.40, and 3, 2 will become -0.4, -0.6. And maybe in this case, I could just come up with all of these by visual and mathematical reasoning. I can kind of just count backwards from the origin and figure out where it'll end up in clip space. But if we think about it, we could also reduce that to subtract 5 and then divide by 5. So one way you could get all of your vertices into WebGL clip space is to iterate over all of them, subtract 5, and divide by 5. But there's a better way, and it's something that graphics is particularly well suited to, and that is linear algebra. Linear algebra is a discipline by which we can transform one whole coordinate system into a new coordinate system. So if you think about it, what we've done here is translated our whole coordinate system down to the left by 5 each, and then scaled it down by a factor of 5. Now I'm going to do something very hand-wavy and tell you that the combination of that translation and scale is represented by this matrix here. We call this a projection matrix because you can use it to project coordinates from one coordinate system into a new coordinate system. You may notice this is a 3-dimensional matrix. Again, like before, the extra coordinate is kind of a linear algebra trick, but we're still just interested in the first 2 components of its output. So now if we multiply each coordinate by the single projection matrix, you'll end up with all of the right coordinates projected into clip space. And by the way, all this matrix multiplication is going to happen in the vertex shader, because remember, the vertex shader is when the vertex gets placed into WebGL clip space. So you can put positions in your vertex buffer that are kind of way outside of WebGL clip space in your own coordinate system, and then attach a single uniform matrix to the shader program that's going to represent your projection matrix for all the vertices in space, and then just have the shader do all of the projection math for you. Now I'm going to do one more very hand-wavy thing and tell you that the reason this is so important is that we can calculate a projection matrix for each tile, individual tile that gets placed on your screen. Because whenever you see a map, it's usually made up of a bunch of different vector tiles, so maybe 6 tiles or 12 tiles or 20 tiles, depending on your viewport size. And we render tile by tile, and for each tile, we calculate a projection matrix that represents how to translate that tile, which has, in our vector tiles, a coordinate system from 0 to 8,192, into these individual small squares in the -1 to 1 clip space on your screen. So to recap, the things you need for rendering are a vertex buffer with a bunch of individual vertices, where each vertex is made up of different attribute data, which is almost always including, but usually not limited to, some position coordinate that will help us position this vertex in space. An index buffer, where each triplet represents a triangle, and each member of each triangle represents an index into the vertex array. A vertex shader and a fragment shader, which might look something like this. You'll notice in this example, by the way, I added this uniform mat4u matrix line, and that's how we would have attached a single projection matrix to this shader program, and it will be used for all of the vertices processed by this vertex shader. So now we can just multiply each position by the uniform matrix and end up with the positions in clip space. A few other things I didn't mention too much: uniforms, textures, depth, and stencil state, which you can ask me about afterwards. So how does this apply to maps? I think it's useful to think about, what is a map rendering engine anyway? Any kind of rendering engine that's built on top of a graphics API like OpenGL or WebGL is basically really just an abstraction layer. So a map rendering engine is an abstraction layer between map designers and the low-level GPU commands. We build Mapbox GL so that you, a person who wants to use maps, don't have to figure out how to translate map data into triangles yourself. So that's what Mapbox GL is. A map designer thinks in terms of complex shapes, points, lines, and polygons, and then output colors and widths. And the GPU thinks in terms of triangles and shader programs. So a map rendering engine is what translates from map concepts into triangles and low-level GPU commands. So if you've seen a Mapbox GL style sheet, you'll know it's this big JSON structure. It's got a lot going on. But really, these top parts here are just more or less metadata that tell us things like where to download tiles from, where to download sprites from, where to download fonts from. The real bread and butter of a Mapbox GL style sheet is this layers array, because the layers array is essentially just an ordered list of draw commands to perform. Each Mapbox GL layer type corresponds to a specific way to tessellate that data into triangles and a specific way to draw that with shaders. So an ordered layers array is really just an ordered list of draw calls. So as you probably know, our basic geometry types in the geo world are points, lines, and polygons. So these are the raw input types that map designers are usually working with. You'll notice none of them look like triangles. And the outputs that a map designer expects to make with these are things like fills, lines, circles, symbols, fill extrusions, heat maps, hill shades, raster layers. Those don't come from vector data, so I didn't include them here. But one thing Mapbox GL has to do is to figure out how to translate from all these different input geometries into a bunch of triangles, and finally into these output types, which can happen in all these ways you would naturally expect, and then a few others as well. So basically, the layers array in the style sheet says, based on this input data, which per layer is all of the same type, point, line, or polygon, make a bunch of triangles, and then render them into this output type. So I'll show you a few examples of what this looks like. Here's a polygon that we want to use for a fill layer. This is Virginia, which is where I'm from, or most of it. Here's what it looks like when you slice it all up into triangles. This is using a tessellation library called earcut, which Vlad wrote. I'm sure you've all heard of Vlad. And this is what it would look like when you fill in all those triangles. It looks like a filled polygon, like you might expect. This is a line geometry. I actually didn't make this up. This is the real geometry of Lombard Street in San Francisco, very famous street. Here's how we tessellate lines. We basically make each straight segment of a line into a quad, a little rectangle with two triangles. Sometimes, depending on the curve, we can add a little pie slice, which is a triangle without a complementary side. And then we fill in those to make lines with a few pixels that are blurred for anti-aliasing. We could also make dashed lines or outline lines using pretty much the same techniques. Raster layers don't come from vector data, but we still need to draw triangles in order to place them into our WebGL clip space. So to place, say, a raster tile like a satellite tile, we draw a quad, which is two triangles like this, and then we copy the raster pixels into the triangles in the raster fragment shader. Circle layers typically come from point features. So here's a point feature, and then to draw a circle, we also want a quad. So we just project out diagonally in all four directions from the source point and make those into triangles. And then we can use some fun fragment shader math where basically we assign each vertex a position as if it's a Cartesian coordinate where the source data is the origin. And then assign those to varying so that we can interpolate the position of every fragment and measure the distance from the origin to that fragment. And if it's long enough, it's considered to be outside of the radius of the circle, and we draw it transparent. And if it's inside of the radius, then we draw it opaque. Symbol layer tessellation works similarly in that when we know where to place a symbol, we tessellate each symbol, which is each glyph or letter, into a quad again. I want to note here that symbol placement is kind of its own form of dark magic, and there's a lot of computation dedicated to it because symbol layers are the one type where you usually don't want a one-to-one mapping of source data to rendered data. And that's because you have labels of variable length, and it's really hard for humans to read overlapping text. So we calculate the ideal positions of every label in your map and then drop all the ones that don't fit. So I'll show you what that looks like a little bit. Here, every red circle or box represents the ideal placement for a label that just won't fit on our screen. So we have to calculate all these positions and then drop most of them. And you can see we have to constantly recalculate on fractional zoom levels. And every time we pass an integer zoom level, we load new vector tiles and do a ton more placement. But anyway, once we know where to position a glyph quad, we read in the fragment shader from a texture that has these kind of ghostly-looking letters. This is actually not a letter, it's called a signed distance field, and what it means is that each pixel in the signed distance field, or SDF, represents the distance from that pixel to the boundary of the rendered glyph. This is a technique that enables nice, smooth, anti-alias glyphs without artifacts when you scale or rotate them. So now we can figure out all the pixels that are opaque enough that they'd be considered inside the glyph and fill those in. Another cool thing about signed distance fields is that we can just slightly lower the threshold of what we consider the opacity that is inside the glyph. And in doing so, we can make cool glyph halos. Fill extrusions also start with polygon features. Here I'm just using a quadrilateral to make it easier on all of us. And then we tessellate that polygon using ear cut just like we do for fill layers. In this case, it's pretty easy because it's just another quad, but it could be any shape. And then those triangles will make up the top of the extrusion. And then we go around the footprint and add a vertical quad for each side. And then we shade these in the fragment shader. We also attach data about the normal vectors to each vertex. The normal vector is a vector that points perpendicular in space, so out from the walls and out from the roof. And we can use that data to determine the final color based on the light property of the map. There are a few other layer types as well, background layers, which are full bleed layers that don't come from data at all. And then heat map and hill shade layers, those are kind of special cases that require multiple passes, so they're harder to visualize with tessellation. This is my Moybridge slide. This is 108 of the roughly 650 individual draw calls that happen in the single frame of San Francisco in the Mapbox Streets default style. And if you think about our target performance being 60 frames per second, and if Mapbox Streets at this viewport size takes 650 draw calls per frame, approximately, that's 39,000 draw calls per second, which is pretty wild to think about. And I want to note that the single biggest driver of Mapbox GL performance or of any rendering performance is going to be number of draw calls per frame. So as we've established already, the layers array in a Mapbox GL style sheet is essentially just an ordered list of draw calls. So the less layers you're using in your style, the less draw calls you'll have in your style, and the more performant your map will be. Hopefully you saw John's talk yesterday where he talked about how to condense layers into fewer layers using expressions. That's a really great technique for more performant maps. And if any of you follow me on Twitter, you might have seen some bad maps. I like poorly rendered maps because I think that showing the rough edges of rendered outputs kind of exposes how they actually work. So I'm going to finish with some bad maps. I didn't really talk about the depth buffer much, but a depth buffer is where you can write depth values. That is how far each pixel is in space. And you can use those values to calculate for the next pixels, whether they're in front of something or behind something. So in this case, we're not using a precise enough depth buffer, so all of the planes that are really close to each other kind of waver on whether they're ahead or behind, which is why we get these artifacts at tile seams and corners. This is just pretty bad. I'm not sure what happened. Fill extrusions are rendered to a separate texture off screen and then copied back to the map. We do this so that we can make semi-transparent extrusions without showing interior walls. In this case, the texture was copied back incorrectly, so even when we rotate the map, they're still rotating right, but upside down in the wrong plane. This is a bad map I made on purpose to show how the walls of extrusions are tessellated. So in this case, we're just dropping every other triangle, and you can see how many elements go into these shapes. This one I just think looks cool. This is called a triangle indexing bug, which is when the values in the index buffer are off by 1 or so. So you can see a lot of these shapes are still intact. There's a lot of intact walls. And then maybe the last vertex of each feature is accidentally connected to a feature it's not supposed to connect to, and you have these weird triangles all over the place. This is, again, the texture that's been copied back incorrectly. In this case, it's copied back at a quarter of the intended size. So then it just bleeds off the screen in the adjacent quadrants. In this case, the depth reads are inverted, so you can see like all of the values are kind of backwards. The walls that are supposed to come behind a feature are drawn in front of it. Makes this weird kind of physics bending effect. This is another triangle indexing bug. It's really easy to see the triangles here. The left image here is a bad map because the lighting is applied incorrectly, but I think that the middle image is more interesting. This is what a visualization of a depth buffer might look like, where all the darker values represent values that are closer in space to the camera. So this is kind of how a 3D graphics API keeps track of spatial relativity. In this case, we're not clearing the depth buffer at the beginning of every frame. So the depth buffer from the previous frame persists, which means that the pixels that are white here aren't being drawn because they think they're behind something, but what they're really behind is where they were in the last frame. This is where some shader math has gone awry, so all this text has become flipped and giant. In this case, we're trying to copy the extrusion texture back to the map, which is a full bleed texture, and instead we're copying the wrong texture unit. This is what the SDF might look like, so this is the texture that contains all the glyphs in the map. This is a recent bad map. We recently did the Vector Tile 3 sprint to start prototyping on Vector Tile 3 features. One of those features will be probably 3D points and lines. So this is a bad version of a point cloud. If you want to see the good version of the point cloud, I think that Blake is showing off some VT3 work in the exhibition hall today. So I hope you've learned a little bit about graphics programming or map rendering or a little bit of both. Thanks for your time.
All right. Thank you so much. Lauren, I think we have time for 1 or 2 questions. If folks have questions, please raise your hand.
Hi. How much of that data that's in the GPU can be used, like on the way back, for example, for some sort of spatial operation to say, like, I want to find if this geometry intersects this other geometry?
Yeah, that's a great question. So the question is, how much of the data that's been uploaded to the GPU can be used to process in reverse, like to do geometry operations? You could theoretically do that, but there aren't really great spatial geometry libraries to operate on uploaded vertex data, because that data at that point will have been processed into vertices. Additionally, yeah, it's definitely possible, and there are also specific techniques you can do in rendering itself to, like, write values that don't represent rendered values, but rather represent, kind of different numbers. It's very vague, but and basically read from rendered but non-visual outputs to do like comparisons. I don't think that was very helpful, but kind of tricky. There are some graphics techniques to do so, but yeah.
Like with TurfGFs,
yeah.
Like, have you ever done anything with it and have it take like 20 seconds to return?
We haven't tried doing anything with, say, TurfJS, because it would require rewriting a lot of the TurfJS parts that rely on geographical data and not on not on vertices in screen space. But someone could try it.
I'll try it.
Cool.
Great. Other questions?
Hi. I'm wondering to what extent is Mapbox GL JS extensible? Can I write my own shaders? Can I share the WebGL context?
So the question is, can you write your own shaders and share the WebGL context in Mapbox GL JS? That's a very timely question. That's a feature we'll be releasing roughly this summer, is access to the context to write your own layers with your own shaders and your own tessellation.
Great, maybe one more question?
How do you think about and measure performance on all the different devices out there? What's your minimum bar, or do you test live, or how do you determine if something is too expensive to put out there for everyone?
Yeah, great question. The question is, how do we benchmark performance and determine if something is too expensive? So we have a pretty extensive benchmarking suite that measures like time to render for aggregate styles and also for individual styles, and measures different individual parts of tessellation, or basically creating vertices versus rendering. Our target performance is always 60 frames per second. As you saw, that kind of depends on number of layers, so you could make a really very unperformant map with tons and tons of layers. But yeah, we shoot for 60 frames per second for default styles and like good maps, and we kind of measure everything against existing benchmarks to try not to degrade any performance.
Okay, awesome. Thank you so much, Lauren. Please give Lauren another round of applause.